Hello, everybody. Why does a computer represent the number 13 as a string of zeros and ones? To be able to answer that question, we'll first need to understand the difference between analog and digital information, how circuits physically represent a 0 and a 1, and how those bits combine to form numbers. And then we'll do some practice questions converting between binary, decimal, octal, and hexadecimal. Also, this video will serve as kind of an introductory mini lecture to most Digital Systems 1 courses, which is a core fundamental electrical engineering course. So, let's begin. Why does a computer represent the number 13 using only ones and zeros? So, first you need to understand the difference between analog information and digital information. Now, computers can be built both with analog and digital information, but they both represent very different things. Analog information is a continuous strand of information. However, digital information uses distinct separate values like high, low, high, low, high. This is important. This is you're going to see how this information is important in the next slide. So, in terms of why computers represent zeros and ones. So, in computer language, logic 1, which is a 1, would represent a high voltage range. So, in this little chart I have here, it would be 3 to 5 volts would be our high voltage range, and logic 0 would represent a low voltage range, so roughly 0 to 1 volts. The reason why computers choose to represent um, information, digital information, opposed to analog information, is that it kind of eliminates some of that, like I want to say like voltage fog or noise. It essentially like doesn't include this transition region. Digital information will not include this transition region because it's more of a logic 1, logic 0 scenario. It's a high voltage range or a low voltage range. So I think that just allows for like more simplicity in like just the building of circuits and whatnot. Whereas with analog information, like it would just be like a whole like different ball game. So now, why computers are going to actually use 1 and 0? Because as I said, they only interpret a low voltage range or high voltage range. So from bits to numbers. So a bit is a binary digit, either 0 or 1, which or either a low voltage range or high voltage range. So binary is a numbering system, and the way this numbering system works is that it uses something called positional notation, where it essentially denotes the value of the base to a position in the number, if that makes sense. So this is going to make sense as like we continue to like go through the slides and I go through some practice questions or whatever. But essentially, binary is a base 2 number system, which only uses 0, only uses 1, and each number in a binary string of numbers is each going to correspond to its own position. So like for example, um in a whole number, the positions would be like 0, 1, 2, 3, or as I have it drawn out here, it'll be the because binary is a base 2, right? It'll be the base to the position, the base to the position. So it'll be like 2 to the 0, then to the 1, then to the 2, then to the 3, because that is like the actual position of the number. And then if you were to actually calculate it out, you would get the number 13 here, if that makes sense. Again, things will start to click more as we like continue on, but to just do a quick summary, computers can represent the number 13 using a string of binary numbers because of the fact that most computers choose to use digital information, which represents numbers in discrete values, which would be logic 1, which is a high voltage range, or logic 0, which is a low voltage range. With using the binary numbering system and positional notation, you're able to easily convert between 13 and the base 2 system, which is just more simplistic. This is just easier for the whole purpose of binary is that it's easier for the computer to understand opposed to using a base 10 system. Okay? We represent 13 as binary because it's easy for the computer to understand. Okay, that's all you need to know. So, this one value 13 corresponds to 4 different number, not corresponds, but is can be we can calculate its equivalent in 4 different numbering systems. Okay, so the normal numbering system you guys are used to is base 10, which uses digits 0 to 9. We also have binary, which I just introduced you guys to, which uses logic 1 or logic 0, or a high voltage range and low voltage range. Binary is a base 2 because it only utilizes the digits 0 and 1. We also have octal, which is a base 8 numbering system, which only uses the digits 0 to 7. And then we have hexadecimal, which is a base 16 numbering system, which uses digits 0 to 9 and numbers A to F. Now, numbers A to F, they represent the digits 10 to 15, okay? So like A would correspond to 10, B would correspond to 11, C to 12, D to 13, and then E to 14, and then F to 15. Okay, as to the exact purpose of octal and hexadecimal, I'm not exactly sure what the exact purpose of octal and hexadecimal are, but this is just a surface level explanation. So, this decimal value 13 can be represented throughout these 4 different numbering systems, and you can circulate between all of these different numbering systems by simply using, I believe it's called positional notation or polynomial expansion. Now we'll get into some questions. Okay, everybody. So this is, I'm going to be just going over some binary conversion questions. And we're just going to be converting between the 4 different numbering systems: decimal, binary, hexadecimal, and octal. These are similar level questions that you're probably going to get like on your first day of like your digital systems 1's class, and like these are just foundational skills. You guys need to know how to convert between the 4 numbering systems. It'll make your life a lot easier, and I'm going to show you some tricks. So, to convert this number from binary to decimal, we are going to use positional notation. And positional notation is going to be the, sorry, this is the wrong thing. Positional notation is going to be the base to the power of the position. Okay, so we know that for one, binary is a base 2 numbering system. So we know that all of our positions or all of our ones are going to be base 2. And it's just going to be a matter of counting from 0, 1, 2, 3, 4, 5, and then it's gonna be like after the radix point. And it's normally you guys would call it a decimal point, but it's actually not going to be called a decimal point because that, like, a decimal point only applies to the decimal system. So if we're talking about a non-decimal numbering system, like a base 2 numbering system, it's called a radix point. And then after the radix points, the positions are going to go -1, -2, -3. Now, please note, in a normal digital systems 1 class, there will be no calculators. However, for the sake of like simplicity and just not drawing out this video for like 100 years, I am going to use a calculator. But you should be doing like your addition by hand, subtraction by hand, multiplication by hand, long division by hand. I can make videos on how to do that. I probably will. So, how to convert this number to decimal. First, you're going to be using polynomial expansion to expand the base and the position of the number. So we know that the position is going to be 0, 1, 2, 3, 4, 5, -1, -2, -3. So what that's going to look like in terms of the number is it's going to be the radix point. I'm just going to start with the -1, with the negative portions. So it'll be 0 to 2 to the -1 plus 1 times 2 to the -2 plus, sorry, this is wrong, plus 1 times 2 to the -3. And then on this side of the radix point, it is going to be 2 to the 0 times 1. And then we're going to do plus 2 to the 1 times 0. And then we're going to do plus 2 to the 2 times 0. And this can get pretty drawn out. So, and then plus 2 to the 3. Oh, nope. 2 to the 2 is times 1. 2 to the 3 times 1. And then plus 2 to the 4 times 0. And then plus 2 to the 5 times 1. So 0. So 1, 0, 1, 1, 0, 1.011. Great. Now, luckily for us, all of the 0 values can just be canceled out just because of like the multiplication. Anything times 0 is 0. So that makes our life easier. And in terms of the actual values, okay, 2 to the 5, that is going to be, okay, 2 to the 5, that's going to be 32 plus 2 to the 3 is 8 plus 2 to the 2 is 4. And then plus 1 times 2 to the 0, which is going to be 1 times 1, which is 1. Okay, you guys understand what I did there? I did 1 times 2 to the 5, which is 1 times 32, then plus 1 times 2 to the 3, which is 8, then plus 1 times 2 to the 2, which is 4, and then plus 1 times 2 to the 0, which is 1. 1 times 2 to the 0. So then after the radix point, we're going to do 1 times 2 to the negative 2, which is 0.25. And then we're going to do plus 1 times 2 to the negative 3, which is plus 0.125. So we're just going to do addition now. Okay, so 0.25 plus 0.125. And that is going to be, after the radix point, it's going to be 0.375. And then we're just going to do 32 plus 8, which is 40. And then 40 plus 4 is 44, plus 1, that's 45. So this number, So this binary number right here can be represented in this decimal number right here by using polynomial expansion and addition. You will have to know how to do this by hand, so you should practice doing this by hand to brush up on your arithmetic skills. Okay, and this will be our second question, where we need to convert 54.6875 base 10 to binary. So essentially the way we're going to solve this question is we're going to do the whole number portion first and then the decimal portion after. So to do the whole number portion, we essentially need to constantly divide by 2 or constantly divide by the base that we want to get to. And then for this decimal portion, we're going to multiply by the base. And you're going to see how this all plays out. For the whole number portion, I am going to do the division by hand because I wanted to show you guys like a more methodical way, more just like mind-numbing way that you can solve this question without really having to think about it. So to begin with the whole number portion, we're going to do 54 divided by 2, and we're going to do some long division. 2 goes into 5 twice, 2 times 2 is 4. Minus 4 is 1. We're going to bring down the 4. 2 goes into 14 7 times. 2 times 7 is 14. That's a 0. Whatever answer you get for your long division, that is going to be the value that you insert here. Now, whatever value you have on top here, that's going to be your next value. We're going to keep going until we get to 0 or 1. We're going to keep going until we get a value of 0 at the top of our long division, or until we get a 1 in our like area here. So 27 over 2. 2 goes into 2 once. 2 times 2 is 2. That's 0. Bring the 7 down. 2 goes into 7 3 times. 2 times 3 is 6. That leaves us with a remainder of 1, which is what we're going to put here. Then we have 13 over 2. So we're going to do 2 divided by 13. 2 goes into 1 0 times. 2 goes into 13 6 times. 2 times 6 is 12 minus 13, that's 1. Then we're going to do 2 over 6. 2 goes into 6 3 times. 2 times 3 is 6. Remainder, 0. Then we're going to do 3 over 2. So 2 divided by 3, 2 goes into 3 once. 2 times 1 is 2. Remainder, 1. Okay, now 1 over 2. We're going to be 2 over 1 right here. 2 goes into 1 0 times. 2 times 0 is 0. Remainder 1. So you see how I have a 0 at the top of my long division, and now how I have a 1 being divided by the 2. This is your indication to stop. Now once you have this number, you are going to chart it from bottom to top. So essentially our whole binary number 54 is 1 1 0 1 1 0. Okay, now I am going to do the decimal part. This part I am going to use a calculator for, but you would have to, like, write out the long division, the not long division, the multiplication by yourself. So essentially what we're going to do here is, we know our number is 54.6875. What we're going to do is we're going to take this decimal portion here, and we're going to take 0.6875 and multiply it by 2, and whatever value is here will essentially be like the number we chart down. So let's just start. So 0.6875 times 2. Okay, so that is 1.375. Remember, we're gonna take this value here. Okay, guys, we're gonna take this value here. We're gonna chart it down. Then we are going to take this decimal here, 0.375, and multiply it by 2 again. So 0.375 times 2. Okay, that gives us 0.75. I'm gonna put my 0 here. Then you already know the same process. 0.75 times 2. That gives us 1.5. We're going to take this value again, put it over here. Then we're going to do 0.5 times 2. 0.5 times 2. And that gives us 1. And we're going to chart that 1 there. Once the decimal portion gets to 0, you know you're done. In some questions, it won't be a clean decimal. It'll be like maybe like an endless decimal, or one that cannot cleanly be calculated to binary. If that's the case, just work until you have 6 binary number decimal places. So with the whole number, we read it from bottom to top. For this decimal portion, we are going to read it from top to bottom. So with this information, our final number is 11011.1011 in binary. This is our answer right here. Okay, hello guys. So this is our third and final question. Convert the number 7d3 base 16 to binary, then convert the binary result to octal. Believe it or not, this may be our fastest question to complete so far. So essentially what it's asking is to do a hexadecimal to binary to octal conversion. And this becomes really easy once you memorize the table. Granted, there are other ways to solve this question without like memorizing the binary table for hexadecimal, but man, it's really worth your while, and it will really save you a lot of time. So, the table that you guys need to know. You guys need to know this is the octal table. This is the octal table right here. So I'm gonna fill out the table for you guys. In terms of like memorizing this table, like just try to write it out. By the time you get to like your 50th shot, you'll have it down. And it's also useful because when you look at like binary numbers, you can kind of just tell like what the equivalent is now. So 0 is gonna be 4. So basically the way hexadecimal represents binary numbers, it uses four numbers. So I'll just write out the hexadecimal number table, and then I'll write out the octal one, and you guys will be able to kind of like do your own comparison and see the similarities. So 0 0 0 1 0 0 1 0 0 0 1 1. I forgot 4. I forgot 4, guys. Forgot 4. 0 1 0 0 0 1 0 1 0 1 1 0 0 1 1 1 1 0 0 0 1 0 0 1 1 0 1 0. Okay, I'm gonna stop talking. It's probably annoying. Okay, so this is our full um hexadecimal to binary table. I'm also gonna just write out the octal table for you guys. Okay, so as you can see, the octal table is basically the hexadecimal table, but it just stops at number 7. You can see the difference is that it uses 3 binary digits opposed to 4, but you could see that after the first digit, everything else is like basically identical. This is why I recommend that you memorize the hexadecimal table opposed to the octal table, because like if you could write out this full table, you can do any conversion essentially. And also too, like if you have like some long like drawn out binary number, just knowing this like hexadecimal table will allow you to like go from binary to hex to decimal, which like once you've memorized like this table is way faster than going like straight from binary to decimal. And if you don't believe me, you could try it, especially when you're doing things by hand and you have like this whole long drawn out binary number and you have all these polynomial positions. Way faster to convert it to hexadecimal and then convert it to binary from then, to decimal from then. So the number 7D3 to binary, then convert it, the binary result to octal. So basically, we're just going to write out our numbers normally. So our number 7 is 0 1 1 1. Our number D is 13, which is 1 1 0 1. Our number 3 is 0 0 1 1. Okay, so this is our hexadecimal to binary. Now to convert our binary result to octal, we're essentially just going to do from the radix point, because technically like this number has a bunch of zeros behind it. From the radix point, we're gonna group in groups of 3, and then we're just gonna look at our table here or here and just write the corresponding number to the group. So okay, so 0 1 1, that's 3. 0 1 0, that's 2. 1 1 1, that's 7. 0 1 1, that's 6. So technically in octal this should be 6 7 2 3, if I'm correct. Wait, this is not 6. This is 3. 6 is 1 1 0. Okay. 3 7 2 3. This is our answer in binary. This is our answer in octal. And this is how we solve this question. Convert 7D3 in hexadecimal to binary, then convert that binary result to octal. I hope you guys enjoyed the video, and I hope this served as a kind of good introduction to digital systems and binary and computers and all that. And I'm gonna try to make more videos covering the full scope of the Digital Systems 1 course and what you're gonna need to know. And thank you. Don't forget to like, subscribe, especially if you've made it this far. Like, follow the socials, follow the LinkedIn. I'm gonna, you know, start grinding out those um, other social platforms and whatever the case may be. And if you have any questions, you can also ask me on Instagram. Or if you have any constructive criticism, also, I will. Everything is appreciated. Um, yeah, thank you.